So just to recap, what I'm trying to do is write an assembler for the Game Boy. And in the last stream, what we have started is we've hard coded a GBASM file into our WinMain to use. We use the Windows API to open that file and then read a 4 kilobyte chunk out of that file. Then we proceeded to go through character by character and try to find a new line so we can get the start and end position of the first line in the file. Um, and then at the end of the stream, I kind of wondered what would be the best thing to do, right? Should I uh, well, the option 1 and 2 were basically sort of the same, just a bit different with implementation details, right? But essentially, it was read 4 kilobyte chunks of that file and process the file within 4 kilobyte chunks. Now, what would be the benefit of this? Well, even on a memory on a machine with relatively low memory, uh, we conserve a lot of memory by not, it's just 4 kilobytes, right? We're just doing 4 kilobytes at a time, which is basically nothing. Well, on modern machines at least, on smaller machines, whatever. But these days, let's be honest, this is my little tool. It is meant for modern operating systems, right? So we're talking Windows 11. There is no way a modern machine like this, with anyone that's serious about doing anything with a machine today, has less than a gigabyte of memory, right? And okay, how big can Game Boy files be? The biggest ROM is 8 MIBs, right? So if we sort of being generous, so 8 megabytes. Obviously, an assembly file will be quite longer because there might be more characters, right? Some Unicode names. There might be a lot of comments in there. So we might end up, even if we're trying to be conservative, like we might end up with a file that's like 100 megs if we do it all in one file. That's nothing, right? Even on a gigabyte machine, that's nothing. Um, so I think instead of trying to be clever and just reading 4 kilobytes at the chunk, I will just read the entire file at once. Um, so ideally, I would look for a Windows API call that is able to give me the size of the file in bytes, allocate that amount of memory, read it all at once, and then start processing it. Because again, like my machine has like actually let's switch to my Windows machine here, right? So even my Windows machine has, let's see, how can I find out? Settings, system, about, there we go. Even my machine has 32 gigs, right? If you have a slightly more budget machine, there's a chance you even have like 8 gigs or 16 gigs of RAM. So holding an entire file, which might be 100 to 200 megs in memory, it's nothing. It's a tiny speck in the overall system resources, right? Now, if I would ever want to use this assembler on a different machine, first of all, we would have to recode it because it's specifically coded for Windows because I'm not using the C runtime, right? So we already have to do a little bit of work there. And if I then would want to run it on, like, I don't know, Commodore 64 or whatever, right, I can still then rewrite the code and read in chunks. I'll try to keep it modular enough to be able to do that, you know. So yeah, let's just do that. So first I want to figure out, is there a no, this is get lost error, apologies. So on these file things, is there something where I can get the file attributes? I mean, there's a file attribute data structure. So there is set file attributes. And we can also set the file attributes when we create the file, but we do not want to set them, we want to just read them, right? So there is get file attributes here. But this is going by file name. Can we get the attributes? Get file information by handle. It creates a pointer to a by handle file information structure. Yes, this is it. Look at this beauty. File size high and low. Okay, let's try and use it, right? Let's keep this struct open. Where was it? It was the oh, come on, I had it. Get file information by handle. So the reason why I prefer this one over the get file attributes one is because we already have the file open, so we already have the file handle. So why should we look up the file name again to see if the file exists, only to get the file information out of it, right? If we can just retrieve it by the handle. So once we open the file and no, hang on, this is read file. What am I doing? Anyways, this needed to be up here regardless. That was okay. So we have created the file. We check whether it is an invalid handle value or not. If it is, what we actually want to do is exit failure, right? Yeah, simply because if the file doesn't exist, we have nothing to do, so we just want to stop. Now, after we open the file, we're trying to figure out how big the file essentially is. So this is where this function comes in. Handle, get file information by handle. What is the return? If the function succeeds, the return value is non-zero and the file information data is contained within the buffer, blah, blah, blah. If the function fails, the return value is 0. And then we can call get last error. Okay. Well, in any way, if this doesn't work, we should probably output an error. What we want is the input handle, which we have already opened. And then we want LP by handle file information, which is just an output parameter. And this is a pointer of by handle file information struct. Okay. So this one, and we call it file info. Right. And we pass it in the address of file info, so this struct can then be populated with the right data that we want. And if this fails, we just fail to read file attributes from this input file name here. Now, once we're able to open the file, I don't see how get file information might ever fail. If it ever fails, I'm wondering if we then should just proceed in trying to read this file, but instead of allocating the right like the right buffer up front, that we then say, okay, allocate 4 kilobyte chunks, try to read the file in those 4 kilobyte chunks, and then slowly expand. But that's something we can worry on later on, right? Not something we need to worry about right now. So now that we have the file info, we can figure out what the file size is. And there is file size high and file size low. Those are dwords, and dwords are unsigned longs. Now, what does high and low mean in this instance? The low order part of the file size, the high order part of the file size. How about we just print those out, right? So let's do printf, and we have LLD. Let's say this is high, and then we have low. Oh, is it just, sorry, it's just UL, isn't it? It's an unsigned long. So let's set a breakpoint here. Oh, it's just U. 14. Okay. What if we... Let's just spam this file a little bit. This is my way of creating a large file. Oh, I think I crashed the program. Whoops. Okay, can I save? Okay. How big are we? 46. 45 megabytes. Okay. It's way bigger than we ever want to read. Wait, did I not have a breakpoint? I don't understand what this high value means then. Because it's a long, it should just fit all into that. Okay. Time for the Googles. Win32. Get size of file. Wait, there's a get file size. How did I not see that? It's right underneath. I didn't see that. Oh my god. It is recommended that you use get file size X. Okay, a handle to the file. Right, we have that. A pointer to a large integer structure. Oh, that's even better. Because we don't need all this other information, right? We really just want the file size. So let's use that. What is p large integer? It's a pointer to a large integer, and large integer is a struct. Right, it has the low and the high part, but what we actually want is just the quad part, which is a long, which is a int64, which is basically size t. Right. Where do I have a size t? I'm wondering if size t is actually that. Yes, it is an unsigned. I see. Okay. Well, we can just change it to this then. We have our input handle right here. And we have a large integer, which will just be size t, size of, you know what, let's say input size. And then we just give the address of input size. Failed to get file size of input file name. Okay. Now we could try and print out the file size. Which, yeah, that's probably 48 megs, right? I think so. Oops. Okay. So now if we do this 61 bytes, let's check if that is indeed actually the case. Properties, 61 bytes indeed. But as you can see, because I mentioned my sector size of the hard drive, which I know by heart for some reason, don't ask why, is 4 kilobytes. And as you can see, even though this file only consumes 61 bytes, on the hard drive it actually takes 4 kibs away. Because again, files are stored by sector and the sector size is 4 kilobytes, so even if you have a file smaller than that, it will still consume 4 kilobytes on the disk. So cool, so we have the input size. Now we can actually have a buffer that's the same size as the input size, which we need to use malloc for, right? This is what I would usually use. We have a size t where we have the input size and we're trying to allocate exactly as much memory as we're trying to read. So in this instance, we would try to read that. I am wondering if I should allocate the buffer in 4 kilobyte sizes as well. Okay, I'm getting ahead of myself. Let's try to write the code with malloc, and then we'll see what the Windows equivalent of this would be, right? So we can no longer have a static size for our input buffer. Instead, what we need to do is allocate it. So we should change this to a pointer. And what we then would do is malloc, and we want to just allocate the input size, right? If input buffer is null, something went horribly wrong, and we actually weren't able to allocate that much. So what we can say is fprintf stdr. Oh no, actually, let's say we do p arrow failed to allocate buffer. Right, this is not the final error message anyways, so let's not worry about it too much. And then we just return with exit failure. Of course, at the end of the program, we not only need to close the handle, but we also need to free the memory that we just allocated. So what we would do is do a call to free and actually free the, not the input handle, sorry, but the input buffer. Although, strictly speaking, not necessary to do this, because the C runtime keeps track of all the allocations that you have done, and if your program terminates normally, that means you return out of this win main function, it will call free automatically, right? It will just free whatever you have allocated. That's one of the main jobs of the operating system and of the C runtime. So technically we do not need to do this, but let's just be nice and do it anyways. Now there's a small bug here, because if there's actually an error with the malloc, we do not close the handle. So what you actually would want to do is close the handle here, but we don't care right now, right? Actually, let's just do it, why not? Same for here. Okay. So now what we should see is, when we go through this, we should see that the input buffer is whatever the file size is. So in our case, it would be 61 bytes. Let's see here, we pass in the input buffer. Instead of input buffer size, what we should say is input size, right? Because we want the exact size of the input buffer right here. And we still return bytes read. That is fine. Okay, we have a breakpoint here, so let's do this. So indeed, input buffer, I mean, it looks fairly small, right? So it is probably 61 bytes. If we check input size, hang on, why do I have hexadecimal values on? Yeah, so 61 bytes. We allocated enough, so we can actually verify that by going into the watch, and let's say we have input buffer. We should be able to index into number 60, and indeed we can. I mean, in theory we can. No, we can index into everything. I'm sorry. I forgot that this is C. This is not. It doesn't actually check whatever you pass in. You can basically do anything you want. Yeah. Okay, and now we're actually proceeding with reading the whole file into the buffer, which we just have done. So bytes read should be 61 bytes as well, and indeed it is. That means input buffer should now hold the entire string. Unable to read memory. Why is that? What? Well, this is peculiar. Okay, let's do input buffer 0. What? Why Why unable to read this? What is going on? Access violation. Huh. Okay, let me quickly verify something with read file. Because maybe reading and writing. Pointed to the buffer that receives the data. Okay, this buffer must remain valid. The caller must not use this buffer until the read is completed. Okay, it needs to be a buffer that's allocated, so why? Why am I not allowed to look into it? Because I shouldn't pass the address. Oh my lord. Yes. Now, there we go. Input buffer. Now, if we open this up, we can actually see this is a line, this is another line, this is the last line. And there you go. This is our buffer. So I'm not sure about these last two characters right here at the end. That's probably, I don't know, end of file or something. I don't know. Whatever this thing is doing, I have no idea. This preview window. But essentially, our buffer is right here. And here in this one, why is it not showing the... It's showing the line endings down here. I'm not sure if you can see that, but we have /r/n/rn, and then a bunch of characters right here. I'm not sure why it's not in the preview window when you click on view. It's the mysteries of Visual Studio. Okay, but we get an access violation right here, again, because I'm taking the address of something that I shouldn't be taking. It is a pointer already, before it was an array. That was my bad. And now if we call free, we don't even have an access violation anymore. Okay, cool. So we're reading the entire file at once. Excellent. So malloc allocates 61 bytes. I was wondering if I should allocate 4 kilobytes anyways, have it in 4 kilobytes chunks, the same as the sector size. So is also, I think, the page size of malloc. You know what? Let's just try that. Let's just see what would happen if we do that. How would we even structure something like this, right? So we have an input file size, and we want to see if this is a multiple of 4 kibs. So what we should probably do is something like size t remainder, and then have input size modulo 4 kibs, right? This gives us the remainder that is over a multiple of 4 kibs. So if our file is 8 kilobytes and something, we would get the something, right? We can then subtract that from the input size, and then we have the chunk of memory that we, in 4 kilobytes chunks, that we need to allocate. And because the something will always be smaller than 4 kilobytes, we just allocate additional 4 kilobytes in the end. So let's see, allocation size in this instance would be input size minus remainder plus 4096, right? Because we're adding another 4 kilobytes. And now we can allocate exactly at minimum 4 kilobytes, and it's always going to be aligned on 4 kilobytes. So then instead of input size, what we can do is allocation size. We still want to have the input size because that is the actual amount we need to read from down here. So this is still the same, but the buffer is just slightly larger, that's all. Although I'm wondering if we just say read the allocation size, what would happen? You know what? Let's figure it out, right? That's what we're here for. So let's see. Allocation size for kib, because the remainder was the 61 bytes, right? We can make a slightly bigger file later on just to see what would happen. Read result actually worked. That is fantastic. And if we look at bytes read, it still read the 61 bytes. So we can just specify allocation bytes, whatever. Doesn't matter. It does the right thing. And then we just roughly need to see if bytes read is actually the same as the input size right here. And if that is the case, we know that we read the entire file, right? Cool. So before I try to replace malloc with whatever Windows needs for memory management, let's try and factor this out a little bit. What do we call this? So we want to read a file. Well, the first thing is the return, right? It can either be successful or fail, so a boolean to indicate whatever happened there is perfectly fine. And then we can just say read file. And the file name will be wchrt. Let's make it const file name. Right. So we want to read this file. So we do the exact same thing. We have the input handle. So we create a file with generic read. Yeah, open existing, cool. And we get the handle. If the handle doesn't exist, we just return false. Then we're trying to get the file size. File size. Right. No, we do not do error handling here. We close the handle if it fails, otherwise return false. Let's call this read whole file. No. Open file, sorry, I'm trying to think how far I want to abstract this, right? Do I want to create my own file handle and pass it around? Do I just want to have one function that opens and reads a file automatically, but that would also mean it kind of allocates, and I don't usually like allocating within functions. What I like to do is have multiple steps where it's like you do the allocation beforehand before you pass the buffer into something where you actually read the file from. Okay, let's make this struct. Hang on. Type of struct file handle, and we call this file t. And what we have here is a handle and the file size. Let's just call it size. So that way we return a file handle struct. File handle. Okay, we have the input handle. What happens if we call get file size with an invalid input handle? What would happen? Let's check this out. So we still have the code up here. So instead input handle, let's just pass in a failed one and see what happens. Right? Let's make a breakpoint here and here. Okay, we're about to call file size x with invalid handle. Fail to get file size of blah 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 blah. The handle is invalid. Nice. Okay. I was just curious. No, this is a bit too annoying. No, let's keep this as an if. So if it is not an invalid handle value, then we are going to try this. And if this fails, we want to close the handle again. Right. And return false. And we can set file size to 0, whatever. No, actually we do not need to set it to anything. That's perfectly fine. So if this is the case, otherwise we just return true. And this is a bit too... just going back to the previous thing, aren't I? So, okay, if the file handle is invalid value, we just return false. Otherwise, we try to get the file size. If the file size doesn't work, we close the handle and then return false. Otherwise, we just return true. There we go. And this is our file opening thing. Okay, cool. Then another thing we can do is we can have void close file, where we just pass in file t file. Right, and all this is doing is calling close handle without any sort of checks on just the file handle. There we go. This will be closing our file. We can mark this as inline if necessary. Don't think it is necessary, but whatever. What? Browsing operations around this macro may fail. What are you on about? I don't care about the return. Do you shut up now? Is it because of the inline? Fine, leave the inline out, whatever. So, and now we can put this in our own header. Let's do that. And let's call this file.h, whatever. Things in there. Instead of that, we can actually say int, whatever, turn 0, turn 0, all otherwise. Actually, let's do that for true. Okay, then we also need to include windows.h. Yep. And this will be include file.h. Cool, because these defines are here and we're including Windows there, the include from Windows here will probably be ignored, right? But we just need to have this in here so the compiler won't complain, and we have some nice, IntelliSense information and stuff like that. Okay, now what we can say is, instead of all of this, what we're doing is we have a file T, which is called imp file, and we're calling our read file no, I have it open file, right? Open file. Open file, the input file name, and this will be address of this one. Yes. Now, if this fails, so it is null, we can do the same thing as before. We're just saying fail to open input file, and then just print out input file name here. Uninitialized memory. Why is this memory uninitialized? Do I have to set it to 0? Are you happy now? You are indeed happy now. Okay. Cool. So now reading and so opening the file and getting the file size is now just one operation. We just call open file, which is just a bit less clutter. Now allocating the actual file size should still be its own thing right here. What I would like to have is sort of a buffer structure, because the buffer size the buffer size and the buffer itself is always a single unit, right? What do you mean has no annotations? Who cares about annotations? What? Oh no! Don't tell me. There is an open file method. What? What the hell? Open file function in winbase.h. This function has limited capabilities and is not recommended. For new application development, use the create file function. Cool, so we have the same name as something that Windows has, which is not great. Oh, man. So what C then is usually doing is like which I don't really like, but you can prefix your functions with some identifier that this is indeed your stuff, right? So I mean, if we want to be simple, we could just say my open file, right? Or but since this is an assembler, we can just say asm open file. I dislike this a lot. Or we can just call this GBA for GB assembler. So this is a GBA file. We can rename the header actually. Let's call this GBA file, right? And yeah, we have a GBA file, and then we can call this GBA open file. Or like this. I don't know. All of it is pretty shit, to be honest. So this would be GBA close file, and we have GBA file. Right. Fantastic. So then here what we're doing is including GBA file. And then this would be GBA file, GBA open file. GBA file is undefined. What did I do? Oh, GBA file T. So I wanted to name this type. Okay. Right, let's create a buffer header. Let's call it GBA buffer.h, and we have if and if. I do not like this pragma once stuff, so I'm always doing this instead. We're calling it buffer, and if this is not defined, we define it. Right, and then we can add our buffer functions. So what I imagine for a buffer, what we need is a type def struct. Let's call it a GBA buffer. And what we want in that buffer is, okay, first, if def if this is defined, Actually, let's not do that. That is nonsense. Let's just include my type def a, right? Type def h. There we go. Daniel. Oops. So I can use the type defs here. It's not something I want to be sharing anyways as a separate code file. So okay. So our buffer will hold a pointer of unsigned chars, which is 8-bit, right? So this will be our data, and then we have the size of the data. So std.h, I think, right, for size t. And then we have buffer t. Let's say this is GBA init buffer. And what we need is a GBA buffer t thingy right here as a result, but we also want the size. Actually, you know what? Why didn't I do that here as well? Include CRT, because we don't share this anyways, whatever. We can just do std_bool.h right here, and instead of doing this whole int nonsense, we can just say bool. Right, it's there for us to use. Let's just use it. Whatever. So, and now we can do the aligning of these 4 kilobytes. If we actually allocate the chunk, we can just put that right in here. So we have the size, which will be a remainder. Then we have the actual allocation size, right, which will be the size minus the remainder plus 4 kibs. We should add a to-do in here. Actually define alignment size, right? Actually call this sector size. And actually what we should maybe do is have it like this. Cool. So this is nonsense. So then we call malloc with the allocation size. We return the input buffer, which should be in buffer data. If buffer data is null, we just return false. Actually, what we should do is we should be doing, instead of allocation size, buffer size, right? And then we just return if this is null, it's true, otherwise it's false. Cool. And then we could do the same thing with GBA free buffer, GBA buffer t. And we just call free data. Cool. Now this way I don't have to keep separate track of the size that I've allocated and the actual data. I can have that all in a nice struct, sort of abstracted, not quite, but whatever, let's not get too hung up on this. And so basically we can replace this code right here. We can just say we have a GBA buffer, T buffer, and allocate everything to 0. If GBA, actually we should also include that file, right? GBA buffer.h. So if GBA buffer init, or did I call it init buffer? Names are hard. Oh, come on. There we go. Okay. So the size that I want is from input file, the actual size of the input file, right? And the alignment size I choose for kibs, right? And the buffer will be just here. If this fails, we need to call close handle. Actually, no. We need to call GBA close file and pass in the input file and return exit failure. Okay. We can also specify a p-error right here if we so choose. Cool. Okay, now let's make this compile with the file reading down here. So for that, I need to pass in the input handle, so this will be just input file.handle, right? The input buffer will be, actually I should name this input buffer, will be input buffer.data. The size we're trying to read will be input buffer.size. And then here we also have input buffer.data and input buffer.size. And instead of free and close handle, what we want to do is say GBA close file, the input file, and GBA free buffer, the input buffer. Cool. So this will compile and still do exactly the same thing as before. There should be no really weird surprises. So we're still reading the input data, right? Bytes read is still 61 bytes. So this all works still perfectly fine. We're trying to read twice until we have the end of the file reached, and then we just close the file, free the buffer, have no errors whatsoever. And now we can build from there. So what I wanted to look into is how to replace malloc with something that Windows is using internally when doing malloc, right? So what would that be? Your guess is as good as mine, or maybe you do know, I don't know. Maybe there's some Windows programmers out there that are watching this, in which case I'm terribly, terribly, terribly sorry. Okay, let's see. Well, it's definitely not something I can find by just looking at the header names, because those header names are absolute nothing burgers to me, right? I don't know what any of this means. So let's just close a few things. Let's close this, this, and this. Get file information, file attribute. We no longer need this. This is file management. So there should be something. There's a page for file management. So surely there need to be a page of memory management. Like let's say 132 memory management. About memory management. Cool. File mapping. Ooh. Well, I'll be damned. I didn't know about this. This might be useful for later on, but let's just not worry. I mean, we can always change code later on and do optimize things, right? But in order to not forget this, this goes into my questions.md. What is file mapping in Windows, right? See this URL. So I like to put stuff in like a questions file. So whenever I have like some downtime or just feel like, okay, I want to read up on something or learn something, obviously off stream, I can just go through the file and then learn about these different things. Okay. Heap functions, heap alloc. Okay, my uneducated guess would be just use heap alloc, right? Allocates a block of memory from a heap. A handle to the heap from which memory will be allocated. This handle is returned by the heap create or get process heap function. So every process in Windows seems to be associated with its own heap. Okay, let's just do that. So I guess what we're doing here then, instead of malloc, what we want is the get process heap. Include windows.h. And get process heap just returns a handle. Process heap. If the function fails, the return value is null, and you can call get last error to get the last error. Okay, so if process heap is null, something went wrong, so we can say return false. Okay, once we have the process heap, we can probably just call heap alloc. Right? We get a void pointer as a return. Okay, so a handle to the heap from which the memory will be allocated. Right, so this will be our heap handle. So in this case, process heap. Right. Then we have flags and size t, which is the bytes. Size t, what is this? This is a ulong pointer. Ulong pointer is unsigned in 64. So that is basically size t. Right? I mean, even C's size t. Unsigned in 64, yes. Whoa. Okay. Flags. What flags can we use? Heap generate exceptions. The system will raise an exception to indicate a function failure, such as an out-of-memory condition, instead of returning null. I don't want exceptions, for sure not. Which reminds me, do I have exceptions disabled? No. Let's disable C++ exceptions. It's probably not the same thing, but it just reminded me that I wanted to do that. Heap no serialize. Serialization ensures mutual exclusion when two or more threads attempt to simultaneously allocate or free blocks from the same heap. There's a small performance cost to serialization, but it must be used where the multiple threads allocate and free memory from the same heap, whenever. Setting the heap no serialize value eliminates mutual exclusion on the heap. Well, this is fine. This is probably what we want because we are not a multi-threaded application, right? So let's just specify that. We are not multi-threaded. And then we just have the size in bytes. Which will be buffer size. And in here we probably just have buffer data. And we should probably cast this to a UA pointer, right? Because we're getting a void. I should probably done the same here, just to indicate what type I'm using, but I guess this is fine. So if this ever fails, I mean, there's a critical condition going on anyways, like you basically ran out of memory, so your system will blow up eventually. The reason why I'm saying this because here on the return value it says if the function fails it does not set last error, so we cannot call get last error, but we can call get last error on this. So I might just be able to call it after this anyways. Yeah, it should be fine. And then it's instead of free, what we need to be doing is saying heap free, right? We need to specify the process heap again. Okay, fine. So we're getting the handle. If it is not null, we can say heap free process heap. Oh, there's flags as well. Heap free. Right, you can specify the no serialize again, which we should probably do. And then we can do buffer data. I mean, we can also return a bool, to be honest. Why not? So instead of stdlib, what do we need? Std bool, right? Return false, return this, okay. If this equals null, return false, like early termination, and then we have heap free, which will return a bool. Kind of like that more than these returns, to be honest. This is always a bit just reads a bit nicer. Okay, so now instead of the instead of using the C runtime, we are actually using just Windows. We can probably do this by removing this altogether and just relying on Windows here. So we can say size T, right, which is the Windows specification of this. Yeah. What you're using there doesn't really matter, to be honest. And instead of this, we can use Windows bool, which is false, false. How to write unportable code. Okay. Right, so if we run this, it still works. We have an input buffer, which is 4 kilobytes in size. Cool. And we're reading from it just fine. And then we say close file and 3 the buffer, and right, it just works. Let's return bool as well. Okay, you know what? Do the same thing here. This is size T. And this is Windows bool. This way there will be no mistakes made. This one, where you can say return false, otherwise return true. Cool. Let's change these as well. Okay. Superb. So for GBA init buffer, if something goes wrong, we can actually use our print Windows error message that we have right here, and then we can say failed to allocate buffer of I don't know, unsigned decimal, input file size, failed to allocate buffer of bytes. Okay. And then we could also, print out warnings or whatever if GBA close file or free buffer fails, but at the moment we just do not care. Read results. Why are you input file handle could be 0. No, it couldn't be. It really couldn't be. Let's not worry about that error message. Okay. Now we want to read the whole file. Which, I let's just copy all of this, go to GBA file, and let's just say bool read whole file. Right. The file we want to read is file T. And the buffer we want to put this into will be included buffer. GBA buffer.h. Cool. Actually, it won't be the whole file. Let's just say read file. And we'll call read file on file.handle, and we have buffer.data and buffer.size and bytes. Oops. Yeah. Bytes read and file.handle. Why are you complaining? Okay, if read result, actually we can just copy this. Right, we want to return false. Then what we want to do is say, well, if bytes read I'm wondering if I should start allocating in here, but I kind of don't like that. So if the buffer size is smaller than the file size, then we can't read from the file, so we actually just fail. Do I want that? No, this is like very defensive programming again, isn't it? Oh, right, I need to use pointers here, sorry. So if bytes read is not the same as file size, yeah, let's not make this a separate function just yet. Right. Let's just keep that in here. So open the input file, allocate input file buffer, then read the whole file. And we're doing this outside of the loop. We have input file handle, buffer size, data, yep. was wondering, I didn't need to initialize it, though, do I? Let's see. And if reading fails, we print a Windows error. And what we should probably do now is have like a cleanup. If we fail to init the buffer, we go to cleanup file, which will just close the file handle. If the read fails, what we're going to do is we go to cleanup buffer. Which will automatically free the buffer and close the file. And if bytes read is less, it's not equal to input file size, then print out something. Fail to read. Oh, I don't know. LLD bytes from file S only managed to read LLD. So we failed to read input file.size from file input file name. Only managed to read bytes read. That is our error message. What's wrong here? Oh, it's just LD. Okay. Oh. Go to cleanup buffer. And then here, everything went all right, so we return exit success. Okay, why are you complaining? Format mismatch. Okay, let's just do a rebuild and see what it says. Format string mismatch. Well, gee, thank you. So with LLD, you managed to be a bit more specific. Is it just UL or just U? Okay, fine, whatever. So we're trying to read the whole file. If it fails, yeah, we do a bunch of things. Cool. So now that we have the whole... Again? Okay, this is annoying. Hang on. stdio printf. Right, let's be correct about this. So for an unsigned long, we have LL to an unsigned integer. The default precision is L. Okay, so input file size is an int64, right? And an int64, from what I know, should be LL. Are you happy now? No. What is dword? Dword is unsigned long, right? So that would be U, which is L, and L is unsigned long. Oh, for size T we have Z. Okay, fine. Z, happy now. Right, it's the white character one, isn't it? SL. SL. Oh my god. I hate this so much. Let's do a white printf. What do you want? Oh my god, this is starting to annoy the fuck out of me. Oh. Fail to read. Okay, you have a problem with this. Why? Size T is uint64, and you're saying size T. Oh, that's size T pointer. Oh my. Oh, that's for scan. What? Why am I on scan? There, this one I want. Okay. Size T, Z. Unsigned would be U. So UZ. Are you happy now? I'm losing my shit. Is it ZU? It's ZU. Oh my. No, it's still not working. Am I just going nuts right now? Like, based on this should be ZU. Is it complaining about the last U? How to see, ladies and gentlemen. No, for fuck's sake. What are you complaining about? Okay. Conversion size T to D word. Possible loss of data. Unsigned long is the max size. But size T is larger anyway, so there will be no loss of data. So what are you on about? I love how these cannot even be assigned to any... Like, what is this? You click and it doesn't even work. It doesn't jump to the line it actually needs to go to. Incompatible types from size T to P large integer. That's not in here. What are you on about? Okay, let's give Visual Studio a chance to start fresh. Okay, rebuild. Rebuild. Will you look at that? No more warnings. For fuck's sake. $1 trillion company has still warning messages. Fuck my life. Oh, how I hate this tool. How I hate it so much. Apologies. And here we have just you. Cool. Rebit all succeeded. Finally. So now, in this moment, we have the whole file in memory. Yeah, this is where the go-tos screw me over. Shouldn't have done that. So this will be an exit failure. So we're trying to allocate. If we can't allocate, we close the file and go to exit failure. Otherwise, we read the file. If we cannot read the file, I mean, in any way, after we're done reading, we just close the file. Screw it, right? We no longer need it. We no longer need the file handle whatsoever because we have all the data, or the reading failed anyways, and then we don't hold on to the file as well. So yeah, let's just close the file here. However, if we have an error here, what we want to do is we definitely want to 3 the buffer, and then we have exit failure. Right. Same here. We just want to say this and then return exit failure. And the file is definitely closed. Okay. And then here we have return exit success. And we can do this with the result here. Exit failure. Right. Clean up. Go to clean up. Okay. Result equals exit success. And then result. Whoops. Okay, we have read our whole file. close because we are done reading the whole file. And now we can actually start parsing the data that we got in. So parsing start parsing the assembler code, right? Or just, let's say, parsing assembler code. Assembler source code. So again, two options we can do. I can use my find new line function that I already used, right? And then go through all the bytes until I find a new line and then start processing. But I think that would be a bit unnecessary because essentially we can just start parsing immediately from position 0, right? We do not need to find the new line first until we have a chunk and then go back again and then restart processing. Like we can do that all in one go. And basically just process, and whenever we find a new line character, we can just well, start a new line. So whatever we have to do for that. Okay, so in this case, I said I wanted to tokenize things. And the simplest token we can have right now is actually a line, right? So do I want to do that? No, I think we need to start with a few helper methods. So essentially, assembly code can have whitespace characters in front, right? And also we wanted to have the possibility to read Unicode characters. Oh my, okay, here we're coming. But I said I do not want to worry about Unicode characters for now. Well, in any way, what we need to do is for size t I equals 0, this is smaller than input buffer dot size. And no, we shouldn't be doing that. What we should be doing is input file dot size. And R++. And then we can get the current byte, which we just call character. And what we can do is input buffer.data I. Right. And just for the fun of it, no, let's not do that. So now we're essentially iterating over byte by byte. We're fetching the character at the current byte position, and now we can start interpreting. Essentially tokenizing it. One thing that we can see with assembly is like a few tokens that immediately sprung into mind is like white spaces, right? So we need to recognize white spaces because white spaces break up the actual instruction from the arguments. After the comma, there doesn't need to be a white space, so you could still just do that, right? That's another way of separating things. But essentially, white spaces. So, possible tokens. We have white space. Another one would be a comma. Another one we mustn't forget is new line. Let's call it separator. Could be any other separator, right? Comments. Comments are another thing. So code comments. As soon as we encounter a semicolon, such as this, anything that comes after it is part of the comment, so it's no longer valid code, which means we can just ignore it. That goes until we reach, the end of the line via a new line character, or it's the end of the file, right? So, comments. And just because we have these lines, what we can do is have a special token which we will later delete, which is just a word. So let's treat words as a token, right? Words. Now each of these things can have, each of the tokens can or could have a start position and an end index, which is exclusive. Yeah, so it will be one character after the last valid one. Some tokens, like the separator token, which is just a comma, or a new line, which on some systems could be just one character, will just have, a 1 basically. So let's say we immediately start the file with a new line, it would go from 0 to 1, which means there's just one character in there. So let's just start with a token type enum. Right, enum GBA token. And the tokens will be as follows. Let's just follow what I wrote right here, right? So we have new line. Oops, pardon me. We have white space. We have a separator and a comment. And then we have a word to do. This one is just temporary. Should we give them numbers? Sure, why not? We can do this. And then what we can say is GBA token count. Do we need to know the token count? No, I don't think we need to. Never mind. Let's ignore that. And actually what this is a token type, right? Not the token per se. So let's call this token type. And now we can have a little struct that describes our token. So type def struct GBA token struct GBA token T. And what does a GBA token need? Well, it needs the token type, so we know what kind of token it is. And then, as we said, it has usually a start index and an end index, so we can find it within our whole byte buffer. Right? We want to be able to index it and get the information out of that, because we do not want to make copies. We already have the entire file in memory. Why would we make copies of the data again just to process it when we can just use it directly out of that buffer? So now, instead of doing this out here, we can probably have a function which returns tokens. So let's say we can just make it return a copy for now, whatever, it doesn't matter, right? GBA token T. Actually, we can have a special token as well, which is the GBA token EOF for end of file. So we know after we receive this token, there will be nothing else anymore. And this one should actually be 0, 0. And we'll see in a second why. And I don't know if I like an EOF and a file. Right. I'm not a fan of abbreviations, really. So, okay. So let's take this out of here. We have a GBA token, and then we just say, yeah, just next token, right? We want to get the next token. Where do we want to get the next token from? Well, from our GBA buffer, right? And then we kind of need to have well, kind of need to keep track of a position that I'm at, right? So so let's say index. Do I need anything else? Probably not. We'll figure it out. Okay. So in this instance, the index is our starting position. And if the index is smaller than this is where the 4 kilobyte nonsense will bite me in the ass, isn't it? Because we don't want the buffer size, we actually want the file size. Oh man, Daniel. Okay, I will rectify that in a moment, because that doesn't make sense holding those two different sizes. Ideally, actually, let me do that real quick. That should be fairly easy. What we can do is say we have a capacity and we have a size. In this instance, capacity is how much the buffer can hold, right? Then we allocate the actual data based on the capacity. And the buffer size is 0 because we have not written anything into it just yet. So then what we can do in read file, which we have not separated out yet, but in read file, this bytes read stuff right here actually becomes buffer.size equals bytes read, and this is called input buffer right here. Right. And we do not want size, we want capacity. GBA, yeah, that is still fine. We want the handle, we want the data, we want to read the amount of the capacity, and then we actually set the input buffer size to however bytes we have read. Okay, cool. So now if we pass this in our buffer, we actually say size instead. And then we say index plus plus. And this will be buffer data index. Cool. So now it's just a matter of defining our, our tokens. So we do a switch over the character, the current character that we're having, and then we know if we encounter a comma. Let's go to the ASCII table again. I like to use this one. So in this case, a comma, this ASCII table maps to Unicode, by the way, as well. So the first section of Unicode of UTF-8 encoded strings maps to ASCII. So a comma would be hexadecimal 2C. So could write it like this, or if we want to be a bit more readable, we can just do that, actually, right? So if we encounter a comma, then we just need to return a comma token, right? So in this instance, pardon me, we say return a new struct, and the struct will be a GBA token, which we need to return. So we are setting the type to GBA token type comma, separator. And then we have a start position, which, surprise, surprise, is the index we are currently in. And the end index, because this is just one character, is index plus 1. There we go. Right, this is C, so give me a moment. I need to refresh my memory on how this works. No, not like that. Okay. GBA token T token, and then we can say return token. Oh, I haven't named them token type. Right. this is token type separator. Why are you screwing over with my formatting? Like, what is this? Okay, so whenever we encounter this, we will return a token. Do we need a default case? Well, no, we're just iterating over it. We can actually just test if this already works, because we're returning a separator, right, with a start and end position, so that should just magically work. I'm realizing returning it like this is probably not the best. Actually, let's just do that and call this bool. Alternatively, I could return a pointer of it, but kind of not nice either. Let's do it this way. So token type token start and token end. Whoa. Wrong button. Okay, and then we can just say return true. And otherwise, if we have iterated throughout the whole buffer, actually, we could have just returned the the token type instead. I think that would actually be nicer. And this all becomes additional info. So what we can say is this is a token info if necessary. Token info struct, right? And then we can say we return a token type. We can have, yeah, that's fine. We're iterating through the whole buffer. When we are at the end of the buffer, the thing that we need to return is simply just the end of file token. Because we reach the end of the file, this is the last token that we'll see. Token info. Sure, let's call this token info or just info. Then we don't need the type, and then we just say start and end is this, and what we're returning is the GBA token type separator. Yup. Okay. What are you complaining about? Expected a semicolon somewhere. Okay. What did I fuck up? Ah, sorry. Yep. Cool. Wait, was this the reason why this? Nope, still doing that. Okay, fine. Okay, let's call this in a loop, and this is now pretty neat because we can say while GBA next token, actually GBA token type, right? type equals GBA next token. We're going to have our input buffer that we're passing in. Our current index, which not quite nice what I'm doing right here, but let's just do that in this way, whatever, right? So index, and then we can get the token info out. If we then so please, so GBA token info t, right? This will be token info. So this while will loop through all the tokens that we're returning until we get a token end of file, at which point it will just stop looping, and then we're done iterating through the whole input file. Hang on, did I forget a... Yeah, I did. Now we could switch over the tokens if we want to. So token type case, let's say we get a token type separator, right? GBA token type separator. Then we can print it out. So separator, and we can specify a start and end position, right? So in this case, start and let's do it in this notation, why not? An end. And that will be in token info, start and token info end. If we encountered one of these separator tokens, what we then can do is set the index. Actually, we need to do that in general, no matter what we receive. So let's do that. So we have a default case right here. There we can say print unknown token, right? And then no matter what token we have, we want to continue parsing after that last token. So all we're doing is index setting it to token info.end, right? Because that will be the next character we need to parse. Cool. So now if we start this, we should see nothing. Well, we see compiler errors. Where's that? Well, it's printf, not just print. Actually, make it a wprintf because we're doing... we are in Unicode mode. So, cool, we see nothing. As expected. Isn't that exciting? So now with the tokens, what we can do is, let's say we have a comma here, we have a comma here, and here, with a space in between. I don't know, let's have one at the end. Actually in the end of here. 1, 2, 3, 4. Okay, so what we should see is 4, actually, let's make it 5. We should see 5 separator tokens appear in our token stream. 1, 2, 3, 4, 5. And there we go. And we also have the exact locations. So from 0 to 1, there's this one. Excellent. Cool. So we have tokenized separators. Now we can do the same with all the other things, right? So let's say, actually new lines, yes. We have this find new line function here where we can actually just copy what we need out of this. So we have line ending LF, right, which is just this. So we can just do case this one. And what we're getting out of this is info start index and info end is index +1. And this is return GBA token type new line. Cool. Now we're doing the same thing with CR, but there is a little bit more involved, as we know from before. Where is CR? It's this one, right? If we have a CR, what we're actually wondering is, well, we need to check the byte after that to see if there might be an LF lurking around, right? So 0.A here. If next is smaller than buffer size, we're still in a valid range. Otherwise, we have buffer data and next, that is the next index, correct. Otherwise, we say index is next. And regardless of what we have here, we basically know what token to return. It will be a new line again, so let's just copy this code. Whoop. So start will be, okay. Info start will be index. And end will be the new index +1. And that is a token new line. Okay, that is new lines done. And if we run this now, we have unknown tokens. That is correct, because we have not actually, written any code to print out the start and end of new lines. So let's just say GBA token type new line, and just do the exact same code as we did with separators. Well, that's not quite nice because we're printing out actually what it is, right? So let's just duplicate the code, whatever. Separator or new line. And now we have new lines. And because this is Windows, you can see the new lines are actually CR followed by LF, right? Actually, I should leave these like this. Oh, without the semicolon, sorry. Okay, there we go. How many new lines do we see? 1, 2, 3, 4. Is that correct? 1, 2, 3, 4. That is correct, because the last line does not have a new line character because the file ends. If we were to start a new line like this, we would see another new line appear here at the end. And indeed, there it is. Cool. So now we can do the same with white spaces. Actually, let's not do white spaces for now, because there's some tricky parts going on there as well. We can do comments now. So let's say define comment character. We said it's going to be the semicolon, right? So if we have a comment character, so let's refresh our memory what a comment actually is. So a comment starts with a semicolon character, and everything after it is part of the comment. So we can actually just ignore it until we reach a new line character, and then our code can begin anew, right? That's basically the next line of code. So in a sense, a comment is a line terminating token, right? It's like a new line, basically. It just indicates, okay, whatever comes after this semicolon is just a comment. Just we're going to ignore everything. So what we then can do is we could play around with like state machines and stuff like that, but I'm just going to hack it in. It's not about being nice code. We just want to get something working, and then we can kind of refactor it later on. So first, our info start will be the current index, right? Now we'll basically have another for loop. So which will be, let's call it end. And where do we start? Well, we start in index +1. If end is smaller than buffer size, then we're just gonna stop. And then we have end ++. So we basically have another for loop where we now iterate over every single character again, because we want to see if we encounter any line endings, right? So that line ending code can be quite simplified. So what we're basically doing is, let's say, switch buffer data end. If it is line ending LF or just the CR, then we for sure know the comment is at its end, right? So we're just gonna break out of this loop. How should I do this? Shouldn't have used the switch, I guess. It should probably be a separate function as well, but I don't want to do that right now, so let's just next char, right? If next char is line ending LF or is line ending CR, then we can say break. Okay, breaking out of the loop. And we should probably have done this because we need to access the end later on. Okay, I explain this in a second. The minus minus right here. It's a bit messy, but once we put this in a separate function, it should look a bit nicer. And then we have info end equals end +1. Yes, +1. Yeah. Token type comment. So we are countering a semicolon. We're setting that as our start index, right? The semicolon itself. We go to the next character after the semicolon and start iterating character by character again. We check if the character is a line ending. Any of these, we don't need to check for the second line ending character because that is what the next iteration of this function will be doing, of get next token. And what we just need to do here, because after we have iterated, no, actually this, I'm sorry, okay, this is absolutely unnecessary. So if we have encountered these, we're breaking out of this loop and simply set info.end to the end index right here. We could just use info end directly in this loop here. Doesn't matter right now. If there is no line ending, then this is the last line of our file. So which means in any ways it's just the end, and then we return the token type comment as well. So we can test that out right now in our input file. So let's say this is a comment, right? Then let's have a bunch of separators, but within a comment, right? Just to make sure that these are not being returned as actual tokens. Let's just remove all the other ones. So if we see any instance of a comment of a separator token, then we know this doesn't quite work. And then the last line, this is the real last line, is also just a comment. Okay, the space here doesn't matter at all. Cool. And again, we haven't finished the print code for this. So what we're doing here is comment. Cool. So, and let's kind of verify that this is correct, right? We have an empty line, so we just get a new line. That's perfectly fine. We do not have any tokens for these. This will be interesting later on. But we have a comment right here, followed by a new line. We don't recognize these words yet, followed by a new line, another new line. Then we have another comment, and we cannot see any of these separators appear in our stream, which is cool, so this worked as well. A new line, again, nothing here, a new line. And then we have the last comment. Sweet. So the last index is 148. Now let's verify that real quick. If this is actually correct. Token info end is 148. What is our input buffer size? It's 148, which means the last index we can access is 147. There we go. We have our exclusive index again. Sweet. Okay, now we can do the same with white space. So white space is a bit trickier in a way. let's go to the ASCII table. Actually, Unicode whitespace. There is a few whitespace characters that we need to watch out for, and we're only going to be looking at at the ASCII range specifically. What we need here is hex 09. So we have 09. That is a whitespace. Specifically, this is the tab. Line feed is 0A, and we do not need to deal with this one because we're using that as a line ending token. So this is not part of our whitespace, right? We have line tabulation, which is 0B. So 0B. Form feed. I think this is also, where is it? Yeah, carriage return 0D. Oh no, sorry, that's carriage return. Form feed we need to do. Yeah, okay, fine. Well, it says this is a line break. Shit. Okay, we might need to expand our line breaks a little bit. But you know what? Let's just treat this for whitespace for now. Whatever. That's fine. Let's not worry about this for now. What else do we have? We have carriage return. Then we have space, which is 0x20. Right. And then that is Latin supplement. So that won't be in the ASCII range. Okay, basically what we need to do is have a big fat to do here. Correctly correctly treat new line and white spaces from the whole Unicode range. So you know what? Let's just do tabs and spaces for now. Let's not worry about the other things. So let's just have tabs and spaces that we're treating as white space. Whatever. Okay, so if we have either one of these, we do not want to report every single tab or white space as a separate token, because imagine we have like multiple white spaces right here. I should actually do that in my actual input file. So if we have loads of white spaces here, we do not want to report a lot of different white space tokens just for this. Ideally, what we would like is just report this as one token and then say, okay, the white space is, you know, this long, right? So for that, we need to do something similar as with the comment characters right here. So let's just copy that code, and then we can say white space. But the ending condition is a bit different. We do not need to break out of this loop for just line endings. We need to do this for every single special token character that we're having, or any other character that, basically any other character that's not a white space. Let's put it this way, right? That's probably easier to justify. So if next char is not a tab, and next char is not a space, then we're breaking out of this. This means our run of spaces is officially over. Yeah, and that's it, I believe. And otherwise, if it is at the end, let's say here, it should just work as well. Okay, that's white spaces. And we can have printout code for white spaces. So whenever we have a white space token, white space okay. Let's see if we are correct. So we have new line. We don't have any of these. What happened to the comment? Oh no, sorry. It's all these white. Of course, it's all the white spaces in my text, isn't it? So we have one white space. How many do we have? 1, 2, 3, 4. Let's see. 1, 2, 3, 4. Correct. Then we have a comment. Then we have a new line. Okay, perfect. Here we have 1, 2, 3. 1, 2, 3. Perfect. Then we have a new line, another empty line. So this is a new line. Then we have the comment. It doesn't count spaces in the comments as well, which is nice, of course. I mean, if you look at the code, it makes sense, but it's good to verify, I guess. We have another 2 new lines right here, and then we have 1, 2, 3, 4. 1, 2, 3, 4, 5. Ah, exactly 5, because we have this whole run at the end, right? And then a new line, and then another comment. Perfect. I mean, as a test, we could just have, a bunch of white spaces and tabs right at the end. Oh, in this editor, I have auto translation from tabs to line endings, but let's just assume tabs work. Whatever. Yeah, white spaces are at the end. Cool. And now the final part, which is the temporary token that I have right here, which is words. So let's count all those single words, right? And display them as a separate token. So how does that work? Well, we have all these special characters where something specific happens, right? If we have any other character that's none of these, then we're starting a new word count, right? So a new word run. So info start is index. And what we return here will be a GBA token type word. Now, how do we determine how long a word is? You might have guessed we're using the same exact code as we did for comments or for white spaces, and we basically do the exact same thing with words. But now the termination of like when does a word actually end is, well, it ends if we have either, a tab, a white space, a comment character, a line ending, either one of these, or it is a separator character. And now you sort of see that we now get like a bit of a sense of what we can refactor later on. These things are quite similar, except for the characters they terminate on. So it would be quite nice to just pass in an array of possible characters, that are the terminating characters, or maybe have just separate functions where we just list them all out, whatever, doesn't matter how we do it. We probably don't need this find new line thing anymore, but probably we'll be doing something similar like this, like similar functions like these, just for these special cases right here. So for now, let's just hack it in. Super ugly, why not? Next char is not, no, hang on, if it is one of these, right? So if it is this, or if it is a comment character, or if it is a line ending CR, or if it is line ending LF, right? Sorry, not and, what am I doing? Right, or it is a separator character. If it is either one of these, we have found the end of the word. So we just assign it, and that's our last token type. So now we can do this. And because we're fun like that, we can also print out the word if we would like to. I think that would be fun to do. Let's see how we can do that. I mean, what we probably need is a char, a string buffer, say 256, whatever. str copy, copy s, and we put it in the str buffer. Size in bytes would be token info end minus token info start, and the source will be our input buffer to data, and then we have str buffer right here. We need to do an strn copy because this is not null terminated, right? So actually what we need to do is size t count, let's, str count, this will be our count. The buffer size is actually 256, and then here we need the count, which is str count. Right, what are you complaining about? Because this is not a white string, but I do not care. How about that? Can I just specify, yo, I do not want the white string right now? Is that possible? Or are you gonna hate me? S. No, it is a char pointer. So S should just work. I just realized something. But let's try and get this string copy to work first. But I just realized basically we do not need to do the iterations right here. What we can just say is as you can see, our token always starts at index right here, right? And so And since we only have words and all these special characters, we can kind of optimize this a little bit. So what we can actually say is info start is the index that we pass in. And then we no longer need to set the start. Right. And then on the default, if it is none of these characters, no, that's a bit, doesn't quite work, does it? Never mind. I don't want to refactor too much right now. I might screw things up because I really just want to get this done to get the words displayed, and then I'm probably gonna end the stream for today. Anyways, so let's see what's wrong. So our first word, let's make this easy by just saying ABC. DBF. Right. Cool. So we expect this. The token start is 0. Yep. And the token end is 3. 0, 1, 2, 3. Right, okay. So our buffer should have ABC, and indeed it does. The dog wants pets. It's very important to pet your dog. Yes. I've been leaving her alone for a bit too long today, so she kind of wants attention now. Yes, I'm quitting my stream soon. Okay. So that works. The display doesn't work because it's a W. What if you just do printf for now and not worry about this whole W shit, right? Jump. Okay, ABC, so this works. So now let's see. Word, well, this is not correct, is it? You just have ABC every time. Is it because the char buffer is right here? Nope. Oh, yes, of course. We don't want to be on data. What we want to do is we want to be on data and token info dot start. So we need to advance the pointer, right? Otherwise, we'll always be at the beginning of the buffer, which obviously is wrong. There we go. That's what we wanted. So we have ABC, DEF. This is a line. Cool. Then we don't have the comments, which are recognized as words. Then we have this is another line. Exactly. Some other tokens. And then this is the last line. Cool. We successfully tokenized our input file. How cool is that? I mean, the code is not the best. Lots of room for refactoring, but that will be, you know, left for next time. Let's just do make this loads nicer, because ugly. But this is the first step on how to, parse our code file and actually do some things with it. So the next step would be, now that we can recognize words, is to have some structure in there, right? For example, we want to recognize specific keywords, like for example, LD or ink. Basically, any of these Game Boy instructions right here. So all these mnemonics should be a recognized keyword. So in a sense, once we have a token type word, we can basically just need to do a check here. Is this a known operation slash keyword, right? So for example, if this is DEA, which is nice because it doesn't have any arguments, right? So we would then have to check, okay, the token word, which starts here and ends there, is the string corresponding to DAA? And if so, we're going to write this specific byte into the output file. Now with some more complicated arguments, it would be like, okay, if this is an, what do we pick? Apologies. Let's do this one. So if it is LD, we know this is a load command, and the load command requires arguments, right? So what we will then do is check if we have another word token after LD, right? Then we would verify, okay, what kind of word token is this? Is this an L, or is this, there's LD with HL, or whatever, all these different arguments basically that it can use. I lost the line. Whatever, let's do this one. So we will check if it is a B. If it is a B, then there might be other arguments afterwards. So we would check, okay, is the token after this word token a separator token? And if it is, we ignore the white space token because, it doesn't need to be present, whatever. And then we just check for the next word token. And this is all that parsing is, right? You tokenize a file, and then you go through the tokens and see if it syntactically makes sense to what you're expecting. And once you made sense out of that, you know what to write into the assembly output file. That's all there is to it. That's how you basically program an assembler. Obviously, there's a lot of other details involved in here, right? For example, for jump conditions, you have things like this, which is basically labels. And then JPC, for example, here can actually jump to a specific label. So if a certain condition is met, we want to jump to this section in code that has this particular label. These labels are user-defined, so they can be anything you want. Well, apart from like special characters or anything, right? In case you could make smileys if you want to. If you want to name a label like that. So at some point we need to have something like, okay, we need to be able to specify symbol names. That's what I usually call them, just symbols. Think of like variables sort of thing, right? We probably have to put that in like a hash map and then store the location in memory of them. So then when we have this jump instruction, we can actually write the right memory address in there and stuff like that. And then there's also special instructions like this. DB in assembly, although I probably won't name it DB, I will make up my own sort of syntax, because that's the beauty of writing your own assembler. You can just come up with your own syntax. Who cares, right? It's for you, so just do whatever you want. There's like this where you can write specific hex code in specific locations in memory. This is how graphics are done. So in this example file here, as you can see, it's called tile data already. So someone has added some comments here, but this is essentially just a tile map of like a specific graphics that will be displayed on the screen. And I think these particular bytes actually just form, yeah, there's the tile map for this. They just form the Hello World kind of logo thingy. Hang on. I had a tab open before. I seem to have closed it. Shoot. There we go. This graphics. So this Hello World thing that you're seeing right here on the screen is basically just encoded in these bytes. So you want to be able to do that in your assembler as well. Another cool thing is these mnemonics that you have here. There's nothing stopping you from giving these different names if you like to choose so, right? So if you're saying like, okay, you have inc L here, and you're too lazy to remember that, you can just say increment shit, right? It doesn't matter what you name your commands in assembly, as long as this always generates the same bytes that the Game Boy is expecting, then anything goes, right? So you can come up with your own names, own syntax, whatever you want to. Adhering to these names is just nice because they are specified in the official Game Boy programming manual after all. So it helps other people that write Game Boy games read your code more easily. But I think I have a solution of where we can kind of allow both, which, yeah, we'll see. But anyways, that's it for today. That's all I wanted to do. We have a basic tokenizer going. And next time we can look in, well, refactoring a bit and making sense out of the tokens. Okay, that's it.